Okay, so welcome back to the formal methods lecture. Last time we looked at this idea of declarative thinking, and we looked at what language can we use, what logic can we use, and the first thing we introduced was propositional logic, where we have basically just these propositional atoms or Boolean variables, A, B, and they have either true or false values. And we looked at the connectives, and we saw that the different operators, they have different strengths in binding and creating formulas. And then we looked at some concepts like semantic entailment and validity. So we said a formula is valid if and only if all possible valuations of the variables make the formula true. And then we started looking at the first tool, but this is what we're going to do now, where we're going to continue. So the first tool we're going to look at are SAT solvers, and SAT solvers basically allow us to solve the satisfiability problem of propositional logic formulas. So we can determine satisfiability. We can check whether there is some assignment to all the variables that makes a propositional logic formula true. So this is just the satisfiability. It's very different from, question is how different is it from validity? Maybe not that much, but in validity, we're basically asking that all assignments make the formula true. And in satisfiability, we're just saying there exists one assignment to the variables that makes the formula true. And then, of course, the SAT solvers, we can use them also in a, let's say, constructive way, where they can compute such an assignment for us. Usually, when we want to use a SAT solver directly, we need to convert the input into conjunctive normal form. Who has ever heard of conjunctive normal form? It's basically a special syntactic structure of the formulas that we can feed the SAT solver. So we usually cannot feed it arbitrary propositional logic formulas. We have to put them into a very specific format. And one other thing that now here, the satisfiability problem is NP complete. Anybody has an idea what this means? Not polynomial, yeah. So what does it mean? So when you look at the complexity of algorithms, then you usually have maybe linear algorithms, and the linear or polynomial or exponential, this means how many computation steps they do in compared to the size of the input. So you can imagine that if you give a very short formula, maybe just the formula P, and you ask, is this satisfiable? Then maybe it only does 2 steps, right? It checks, can I set P to true to make it satisfiable? And then it already says yes. So this would be like 1 step. But how do we measure really the complexity of some algorithm? So we need to relate the computation steps that the algorithm does to something. And this something usually is something from the input. So for SAT solving, we usually say that the complexity is related or expressed in terms of the length of the formula. Or maybe the number of propositional atoms in the formula, right? So if we have many, this means that the number of computation steps that we need to do goes up. The question is, how bad does it go up? How badly does it go up, right? So if the problem was in constant time, so if the time complexity of the problem was in constant time, then it would mean that it doesn't matter how long the formula is, the computation time always takes the same amount of time, which is not the case here, right? We can imagine that longer formula makes it worse. So what about something linear time? This would mean that if I increase the formula by 1, the running time increased by some constant factor. Like, so maybe it's 5 times the length of the formula. Okay, the linear would be very nice. There are some algorithms which are linear. There are not many. Does anybody know some algorithms like a sorting algorithm, where you have given a list and then you try to sort the list. So anybody has an idea what's the time complexity of sorting algorithms? So we heard n squared, we heard n log n. Sorry? For sorting, yeah. So it depends on the algorithm which we use. So there are some algorithms which can do it in n squared, some algorithms which can maybe bubble sort, or and there are some which are better, which can do it in n log n. So n is the length of the list then. So there are some which are better, and I'm not sure if there's anything better than n log n. But basically, this n log n, in SAT, we're even still worse. And we're not even polynomial. So polynomial would mean that we have maybe n squared or n to the factor of 5 or something, which can already blow up quite a bit, right? So this can be a large number. But here we are exponential. So this means that, or well, there is no known polynomial algorithm that can solve this satisfiability problem. So we can probably construct a naive one which matches the upper bound. So can you give me an exponential algorithm to determine satisfiability of a formula? So a formula has variables, right? And the most simple algorithm basically is already exponential in the number of variables, and we can't do much better. We can, of course, improve the algorithm, but the worst case time still gets us to n to the power of 2. So n is the number of variables, and then to the power of 2. So how would we construct an algorithm? If I would give you a formula and ask you whether it's satisfiable, what could you do? You have only Boolean variables, right? Each variable can only have true or false as a value. And given an assignment to all variables, you can basically compute whether the formula is true, right? So if there is a conjunction between true and true, you know it's true. If it's between true and false, you know it's false. Between false and false, you know it's false. So you can basically write a simple evaluator that checks for a formula whether, given a concrete assignment, whether the formula is true or not, right? So you just propagate the solution. Now, how do you find the assignments that make it true? You basically try all of them. And that's the worst case, but we can't do much better. So trying all assignments, this is what basically would be the most simple SAT solver. Now, this is really, really bad. This is exponential. This is taking tons of time. Nobody wants to wait that long. So how come SAT solvers are a thing if the problem itself is known to be that complicated? How could it be? Are they not a thing? Or are they a thing and there are some tricks? So basically, yes, there are some tricks. People have been working for quite some time to find heuristics and try to exploit relations between the subformulas. And if you find some assignments, you learn from these assignments, and then you can use them maybe to block later things that you know you don't have to try anymore. So basically, I think the time complexity of SAT solvers is now, the realistic one is now not really 2 to the n, but more like 1.2 to the n. So it's slightly better. But still, in the worst case, it takes a very long time to check satisfiability of a formula. But yeah, basically, SAT solvers are kind of the working horse of formal methods. So many tools use SAT solvers, and the reason why they use it is simply because people have come up with so many good heuristics and so many performance improvements that it becomes, well, reasonable to use SAT solvers. Okay, so, but this is maybe a slight warning, because what happened last year in one of the project submissions is that a team basically implemented their own SAT solver, which was not asked for in the project, and which was a bad idea because the way they implemented it is basically this iteration-based try all solutions. So if you ever come across a problem that requires SAT solving, use a SAT solver. Don't try to implement your own unless you really know what you're doing. So there are competitions where people from universities all around the world try to compete who implements the fastest SAT solver, and then those SAT solvers usually make it into the basically production tools that we use. So the ones that we're using right now, they are based on decades of performance engineering. And if you try to implement your own, it's really never going to work. And it means that there is some conceptual misunderstanding that you had when you tried to implement something really with exponential complexity without using all these tricks that other people have already found out about. Yeah, so if you have something like that, use an existing SAT solver. Much better idea. Okay, now the question is, can SAT solvers determine validity, right? These tools, they are a bit odd. They only use conjunctive normal form. We will see on the next slides what that is. And they can only do satisfiability. Oh, really limiting, right? The language that we had was full propositional logic, not just conjunctive normal form. And we also want validity because we might want to check semantic entailment. For semantic entailment, we need validity, right? So yeah, question. Do we have to find something other than SAT solvers? Or are we able to use SAT solvers, and are they able to check validity for us? So, and if you say yes, you have to say why. If you say no, you don't really have to say why because or maybe also try to give it a reason. So to determine validity, we would need to check whether all possible ways to assign values to the variables, whether these make the formula true. Okay, let's wait for more answers. If you're still typing your answer, I'll give you a bit more time. Okay, so let's look at some answers. The first one now, well, on the top says, yes, they are iterative based. So what does it mean? We could basically iterate. We could try to find one assignment and then check the next. Or what does it mean? Next one, maybe for using long. Is it the same as the iterative one? So basically, if we let it run for a very long time, we can check whether all assignments are satisfying. I mean, that's just my interpretation. If you have another one, just let me know. So then the top one, yes, because it will check all the values from start to n, and if it satisfies the formula with a certain value, then that means it's valid. So if it satisfies the formula only with one of the values, then it means it's satisfiable, right? That doesn't mean that it's valid. And I think the last one here says also, yeah, because the formula is satisfiable, then it's valid too. So can somebody give me, is that correct? That if a formula is satisfiable, then it's valid too. Then why would we have two different names for it? Something must be odd here. Can somebody give me a satisfiable formula that is not valid? So I'm going to start, we're going to write this down. Yeah. Satisfiable formula that is not valid. What do we need at least? We need at least one variable, right? Which variable should we take? So let's take the variable. No. Take the variable p. Do we need more? Okay, so let's check. Is this formula satisfiable? If I set p to true, it's satisfiable, right? Is it valid? No. So, well, that's what we're trying to figure out, whether we find a formula that is satisfiable and not valid. This is your formula. Why is it not valid? Because if we set p to false, this whole formula is false, right? So this is an example of a formula that is satisfiable because we can set p to true, but it's not valid because we can set p to false. So yeah, I mean, do we have one which is satisfiable and valid? P or Q? Do we really want two variables? This makes things much more complicated. Let's stick with one variable. So P or Q is still not valid because there are some assignments. For example, if I assign both to false, the formula is also false. But yeah, we probably need some operator, right? Because the formula without an operator is not so interesting. Yeah, so let's say P or not P. Now, this thing is satisfiable, right? Can somebody give me a satisfying assignment? We set P2 and P2. Yeah, well, P, it's only one variable, right? So we only have to set one variable to true. So let's set this to true. Then we have true, or doesn't matter what else we have, right? Because true or something is true. So yes, this is satisfiable. Is it also valid? Now we try the other value for P, which is false. So false or not false. Not false is true. So yeah, this thing is false or true, which means it's true. So this means this formula is both satisfiable and valid. Now let's go back to the question. We kind of did some, well, iteration here, right? We kind of checked, let's try it for one value, let's try it for the next value if it still satisfies the formula, right? But iteration is really expensive. How many possible combinations would we have to iterate? If we have one variable, well, it's just two combinations, right? If we have two variables, how many? 4. If we have 3 variables, how many? 8. If we have 4 variables, 16. If we have 5, if we have 10, 1024. Yeah, because it's 2 to the power of the number of variables. So the real formulas that people are handling in practice, I think they're in the hundreds or thousands in terms of the number of variables. So you don't want 2 to the 2000, right? This just sounds like it's a really, really bad idea. So we don't want to really iterate. We do something more clever. So let's, yeah, try another formula. A and B, or I don't know, not A. Is this a valid formula? No. How do we know that it's not valid? Sorry? It depends on the value. Okay, so can you give me, so how do we know that it's not valid? All you have to do is give me one example where it is false, right? Where this whole formula evaluates to true. So can somebody give me one example where this formula evaluates to false? False and A is true and B is false. So let's set A equals true, B equals false. Then we have the AND goes first because it binds stronger than the OR. So A and B, this gives us then, well, it's true and false. This gives us false. And then not A gives us false. And then we have false or false. This again gives us false. Okay, so the trick here was to show that it is not valid. We only need to find a single assignment that makes the formula false. We can find assignments that make the formula true, right? So the trick is, let's just negate the formula. Because if we negate false, we end up with true. So if we negate the formula, not A and B or not A, and then send this negated formula to the SAT solver. If it finds a solution, we have our example that this formula is not valid, right? Because if this thing has a solution, then it gives us our false. So it's not valid. If it doesn't find a solution, then what does it mean? Then it's valid, right? So if it doesn't find a solution, then it means that there's no way to make this thing, this inner thing, false. So it means the formula is valid. And that's exactly how we can use a SAT solver to check validity by negating the formula and then checking that we really get no solution. If we get no solution for the negated formula, then the formula must be valid. Otherwise, we get an example where the formula is false, the original formula is false, and then we know it's not valid. Okay, so yes, we can use SAT solvers to check validity. That's great. Okay, now we managed to get around the first thing. So we said, yeah, limited to satisfiability. No, we can actually also check validity. Now, the second thing, conjunctive normal form. In conjunctive normal form, each formula is a conjunction of clauses. So kind of the outer operator is always a conjunction. And then the inner elements, they must be disjunctions of literals. And a literal is either an atom, so just one variable, or the negation of a variable. So these are some examples. This is an inner clause. It has here 3 literals, and they're all just in a disjunction. So we only use or inside these. And we can have negation of some literals. So this is a conjunctive normal form because the outer operator is a conjunction, and the inner operators are only disjunctions between literals. Yeah, now why this strange conjunctive normal form? Well, you need some kind of normal form, some standard way to read the input, and there might be some other benefits. But now, does this really give us a solution for all possible formulas? And the answer is yes. Any propositional logic formula can be translated to conjunctive normal form. So no matter what formula we write, we can translate it to conjunctive normal form. That's, yeah, sometimes it requires some tricks. And sometimes we get an exponential blow up. So in the worst case, the new formula that we create from our formula can be exponential in the length of our original formula, which is really bad, right? Because we know that, why is this bad? So we already have something exponential here. And then this is the CNF that we're going to feed the SAT solver. And what's the running time complexity of the SAT solver? It's again exponential. So we're basically putting one on top of the other, which is, yeah, not nice. The thing is that in practice, usually these formulas that exhibit this really bad behavior, they are quite difficult to construct. So there are not many of them, but there are. And even if you don't have this really exponential blow up, you might still have other kinds of blow-ups. So what people do in like real practice, when they need to handle these very, very large formulas, they have some translations to CNF that trade off the length of the formula by adding new auxiliary variables to the SAT problem. And then they can do even further trade-offs. There are some translations to CNF that just preserve satisfiability of the formula, but not necessarily all solutions. So they don't preserve necessarily equivalence. So if you want to know whether your SAT problem is satisfiable, you might use a one of those like heuristic translations that then only tells you, yes, your original problem was satisfiable, but I can't really give you an exact solution because I traded it for performance. Did you have a question? No? Okay. So yeah, so the good news is we can still handle all our logic. Bad news is it can be quite expensive. And then the remedy for the bad news is there are heuristics that help us in this translation. Okay, but this really, we are not going to get anywhere near this size where we really need these kind of trade-offs. So for us, all the formulas that we're going to deal with in this lecture, we will just simply translate them to CNF, and they will probably not exhibit this blow-up. And even if they would, the SAT solvers that we use are strong enough to handle this. So yeah, but if you ever come across this, then you can see that there are in the literature a bunch of CNF, this conjunctive normal form translations, that allow you to trade off the size of the formula for the equivalence of the problem. So it depends what you want, whether you really want an equivalent problem or whether you just want something that lets you determine satisfiability or not. Okay, so yeah, all in all, not that bad. We can handle satisfiability, we can handle validity, we can handle all our propositional logic. Now, the only thing is this CNF. Do we really have to deal with it? The answer is usually not, because people have written automated translations from propositional logic formulas to CNF, and then there is a very nice tool that we're going to use. So if you use an off-the-shelf SAT solver, you usually have to do either like use an existing CNF translation, configure it, or have to do the translation yourself. But what we're going to use is Limboole. This is a tool based on some, so the people who have written it, they actually do research in SAT solving. So they know what they're doing. And they wrote this tool, I think, mainly for teaching and demonstrations and for convenience, so that you don't have to translate everything to CNF yourself. And this tool comes with a SAT solver bundled, and it can check validity, satisfiability, and even report some of the solutions. So this is the original website where you can download it for yourself if you want to. And then we also implemented this formal methods playground. Let me check which color is better. Okay, so let's use this default theme. So that's the formal methods playground. Shoaib, the TA for this lecture, he's working on this mainly. And it's based on some, of course, other works that people have done. So it lets you run Limboole in the browser, which is a very nice thing. So for now, you don't have to install Limboole. You can use it in the browser. There's some drop down here where we see different tools. So whether you want to run satisfiability or validity, this is yeah, up to the selection. So right now, if we start just with satisfiability, let's maybe do our formula that we just had here. So we said A and B and not A. So that's the one we had on the paper. So one thing is the code completion doesn't really work. This editor is the same editor as the Visual Studio Code editor, but running in JavaScript. So it does some kind of guessing of code completion, which is not always correct. But yeah, it's a lot more work to actually get the real code completion. You have to host all kinds of language servers and stuff on your machine. So on our server then. But yeah, so let's try this. Run this. Yeah, I made a mistake. I said and B when it should have been. Wait, sorry. This should have been an or, right? Let's switch. No. Here, the formula that I tried to encode was this one: A and B or not A, right? A and B or not A. Sorry. Is it readable? Let me check. I'll just make it slightly bigger. Okay, so now let's run it again. Okay, and it says this thing is satisfiable, and one satisfiable assignment is 1 and 1. Is this the one we had? No, we had a well, yeah, true is fine, right? So you see the syntax is just slightly different. So for the end, just because it's more convenient on the keyboard to type the end like that, that's basically the end, like in most programming languages. The or, like it's in most programming languages, right? That corresponds. The negation, exclamation mark, like you know from other programming languages. So very close. Now we said we can check. We knew that it's satisfiable, right? But we also wanted to know whether it's valid. So and we said we can do that by negating and then running. And then if it finds an assignment, then we know that it is not valid. So and we see here A equals 1 and B equals 0. This should be now, that's the same assignment that we found to demonstrate that it is not valid because we put it in the original formula and we got out that the original formula is then false. So that's basically now our manual way of checking validity, but maybe the better way, we'll just switch to validity and ask it to check validity. And then, of course, it gives us the same answer, right? That it's an invalid formula. And here's an example why it is invalid, because for A equals 1 and B equals 0, it's falsified, right? So yeah, yeah, we can check both validity and satisfiability. And it gives us some examples. There's this error thing. So if we write something that doesn't like, so for example, we have an end without an operand here, then it gives us this error. So we took this web front end from, where is it? Yeah, this guy who implemented it using the original sources. It actually, this thing fully runs in your browser. So it doesn't execute Limboole on the server. There's this thing called WebAssembly, and then there's some cross compilers from, I think, C to WebAssembly. So if you put really, really big formulas, it's going to block your browser. Your browser might crash or become unresponsive. Okay, but all the formulas we use here, they should be fine. Okay, so yeah, we're going to use this tool now and then, and it actually does the main work for us, right? But the syntax is slightly different. So here, negation is the exclamation mark, conjunction is now this and disjunction is the well, or. We have implication, and we have by implication this, if and only if, in both directions, basically So the syntax is described in this README file. And if you want to put comments, they have to start with this percentage sign. Okay. Now, let's have a look at these questions. Just a reminder of validity. So a formula is valid if and only if for all valuations it evaluates the true, and it is satisfiable if there exists a valuation where it evaluates the true, right? So no, here. Now, if I give you this formula and I ask you to select all properties that apply for this formula, is the formula valid? Is the formula satisfiable? Or the formula is unsatisfiable? Now, how do you do this? Well, you could use this satisfiability and validity check. So it also, one thing, if you want to share the formulas that you wrote here, whenever you hit run, it generates a new permalink, and then you can basically send this thing around, and that's why it has these strange names here. That's basically the permalink to look up the formula that you wrote. But now you can use this tool. It's play.formal-methods.net, and then probably the satisfiability is the default one. And back to the, can I put it side by side? Let me check if that works. Doesn't like that? Yeah. So we already have some answers. How did you do it? Did you put it in Limboole, or did you just look at it and the answer came? So maybe we can, just to make sure that everybody gets the right translation of the formula, well, A is easy. For and, that's also easy. Not B. If and only if A or not B. Okay. So this would be the formula, right? And then what do we need to check? To check validity, yeah, I already selected validity here. Where's my run button? Down here. Okay. It says it's invalid, so I probably shouldn't click this. Did the people who selected that it is valid, did you check it using Limboole? Okay, so basically, right, this is the right way to type the formula, right? Should be straightforward translation. Okay, so this formula is not valid. Then is it satisfiable? So let's switch to satisfiability. We don't change the formula, we just run it again. And the output, yeah, it's satisfiable. We only have two variables, very easy, right? Is it unsatisfiable? Now, well, did we talk about unsatisfiability? Anybody has an idea what unsatisfiability means? So unsatisfiable actually means that there is no satisfiable assignment. So it's like the kind of dual to validity because it means for all possible assignments, it's false. So the SAT solver usually gives you SAT or unsat. So let's try to get something. So this one here, of course, if it is satisfiable, it can't be unsatisfiable, right? Because if it's satisfiable, we know there is one solution, and unsatisfiable would mean there is no solution whatsoever. So yeah, if it's satisfiable, it's either satisfiable or unsatisfiable, right? So this means the correct answers are only the middle one. The formula is satisfiable. It wasn't valid. We saw that that Limboole said it's not a valid one because there was some assignment that makes it false. And yeah, if it's satisfiable, it can't be unsatisfiable. So can somebody give me an unsatisfiable formula? Maybe just with one variable. Variable A. Sorry? A and not A. There's no assignment that will make this satisfiable, right? Because we would require that both the scrolling is, well, yeah, maybe that's my, okay, yeah. So here it tells us, well, it's an unsatisfiable formula because there's nothing that would satisfy it. Now, what happens if we negate this? What do we get? Yeah, it will be valid, right? It's not only satisfiable, it now should even turn valid. Yeah. Okay, good. Good. All valid formulas are satisfiable because, yeah, yeah. So if it means that all the assignments make it true, then of course you can pick one of them, and that means it's satisfiable also, yeah. So if you have a valid formula, it's always also a satisfiable formula. This formula was unsatisfiable, and if we negate it, it becomes valid. So unsatisfiable formulas are never valid, but the negation is always valid. Yeah. Okay. So sometimes these relations are a bit confusing, but they really help you when you want to implement something. They might allow you to find some shortcuts. For example, you can use a SAT solver that only gives you satisfiability, but you can use it for validity checking, right? Which is sounds much stronger, but turns out to be the same kind of problem. You just add a negation. I think we had two questions here. So let's look at the second one. This is a bit more theoretic. Don't know why it turned out so small. So now select all the correct statements. All valid formulas are satisfiable. So if your short-term memory is more than 5 minutes, or at least 5 minutes, then you will know the answer. All satisfiable formulas are valid. Some satisfiable formulas are valid. And some valid formulas are not satisfiable. So some would mean at least one, right? Yeah. Oh, you can't see the URL. Something happened. I'll try to refresh. What happens? Yeah, now it's larger again. Okay, so answers are coming in fast because we talked about some of them. Okay. Yeah, we just said all valid formulas are satisfiable because valid means that all possible assignments to the variables make them true. And satisfiable just requires that one of them does. But if all of them do, then of course also one of them does. Then all satisfiable formulas are valid. This way it doesn't work. So if we have a satisfiable formula, this was exactly the one we started with, P. P is satisfiable as a formula, but it's not valid because P equals false would make the formula false. Okay, then some satisfiable formulas are not valid. So to demonstrate this, you would need to find one formula which is satisfiable and still not valid, which we just had the formula P, right? P as a formula is satisfiable, but not valid. So this one is true. And then some valid formulas are not satisfiable. This would basically mean unsatisfiable, right? But that's false, because if the formula is valid, then any possible assignment to the variables makes it true. So that means any possible assignment satisfies it. So of course it must be satisfiable. Let's see. Yeah, so yeah. Very good. Not 100%, but close. Well, here at least the majority agreed. Okay, good. Okay, now we have an example that we can solve with Limboole. So I already, if you want, you can try it directly from the permalink here. So the nice thing about these permalinks is we will use them sometimes on the slides, because then we can already put some of the tasks in here, and you can basically fill them out directly and try to run them. So now the task here would be, we should try to express the sentences in propositional logic, then formulate the conclusion using semantic entailment, then transform it to a validity check, and simply check validity using Limboole. So now the tricky bit is that in Limboole we can't really put multiple formulas at once, right? So if I formulate if the train arrives late and there is no taxi, and there are no taxis at the station, then John is late for his meeting. So if I really want to formulate them here and try them out, I would have to do maybe one by one first. So I could do the first one, then comment it out, then do the second one, comment it out, right? So that's maybe, yeah, not a bad idea. Somebody wants to do the first one? So again, we have to maybe agree on some variables, right? So maybe train late, taxi, and John late, something like that, right? Those were maybe the ones that we had. So who wants to give me the first sentence? So that's train late, sorry? Okay, everybody agrees? So can we check anything about this right now? We can check whether it's satisfiable, right? If it wasn't satisfiable, that probably would be bad, because then we already have a statement that is always false, right? Which is a bit strange. So let's run this. Yeah, it is satisfiable. Should we check validity of this as well? So it is not a valid statement. What would it mean if it was a valid statement? In our context here. If this thing was a valid statement, so no matter how we set the variables, it's always true. Would this help us anywhere in our deriving our conclusion? No, because it's meaningless. If everything makes it true, it's like a trivial statement that is always true. So it's John is late or he's not late, right? That's very easy. I would write John late or not John late, and this wouldn't mean anything, right? Because it's simply true that yeah, he's either late or not, right? So it's if we had something that is valid here, could be that it is, but probably not very helpful then to make any conclusions from it, right? Because it's just saying that yeah, whatever happens, it's true. So yeah, good. So that's the first part. Now, okay. So now, what does it mean that we have a falsifying assignment for our statement here? So let's say this says the train is late and there are no taxis and John is not late. What is that in relation to this sentence? On the logic level, it's a falsifying assignment. But what is it on the conceptual level for us? If you made this statement and I tell you, well, I saw John, the train was late, there were no taxis, and John was not late. This basically can't be. It's a contradiction to what you just said, right? Because you said if the train arrives late and there are no taxis at the station, then John is late for his meeting. So this assignment, this really can't happen. It would be a contradiction. So this would contradict the rule that you just made. So and that's fine. There will be some like invalid scenarios, impossible scenarios. This is an impossible scenario because if the train is really late and there are no taxis, then John must be late, and John late equals 0 can't be. Okay, so that's just some sanity check because we have this kind of here we have like an English sentence and some semantics of it in our minds, and here we have a logic formula which of course has also some semantics like these assignments we see here, and we just have to make sure that we know what is the connection between the two, right? Okay, so now let's maybe we're done with the first sentence, right? Now we should use the same variables for the second sentence. How do I say that John is not late for his meeting? Not John late. Great. Now we can check again. Well, validity. Now a falsifying assignment would be if John is late. Of course, yeah, that's again like a contradiction, right? So that matches with our intuition. Good. How do I wait here? Oh. Now, how do we say that the train did arrive late? Train late. And we check again. Oh, okay. So I think if you click too many times, it gives you a message to slow down. Yeah. Okay. So train late. Yeah, and of course we can contradict this with saying the train was not late, but this would be a direct contradiction with the train did arrive late. Okay. So now the last thing. There were many taxis at the station. So this, therefore, we will ignore it for now. We'll just say there were taxis at the station. That's simply taxi, right? Yeah, okay. So now we have this bunch of formulas. So we probably think that we have encoded each sentence in these formulas. Now, how do we check that we have semantic entailment? Anybody remembers? So we can write down semantic entailment with this this formula up here, comma, this formula, comma, this formula, comma, this formula models taxi or semantically entails taxi. But we had some way, probably have to go back to the slides, or does anybody remember? We had, must be here. So here, what we want to show is this semantic entailment, that given these statements 1, 2, 3, 1, 2, and 3, the fourth statement automatically follows, right? This is the semantic entailment that we want to show. And here on this slide, we have how we're going to translate it to validity. So we take the, third, which should imply the fourth, which should be implied by the, second by the first. So we basically unravel or nest these implications. So let's do that. This means we have to take the first. Let's do it from, start. And let's put it in parentheses to not mess up with the implication. Then we take the second. And the second implies our next one, which then implies our final one. Taxi. And what do we need to check on this? It's said here on the slides that basically, if we want to show semantic entailment, we have to check for validity. What does it mean in like intuitively that we have to check for validity? It means that no matter how, in which way, these formulas on the left were satisfied, the formula on the right then also must be true. And if, of course, if any on the left, because these are all implications, if any formulas on the left were not satisfied, then we don't care about the whole rest, right? So the semantic entailment was any valuation that makes all of the formulas on the left true also must make the formula on the right true. So that's basically this implication. And then we have to check for any valuation. So let's check for this, and it is a valid formula, which means that this conclusion that there were taxis at the station is true. Very good. So now we also were convinced by the Satsolver tool. Good. So should I put this? Oh, did I mess it up now? I don't know. Oh, that was a bit far. What happened to my slides? This was the last slide. So I want to put it maybe, because now we have the solution down here. Okay, any questions about this? Then we're going to have a look at another, this one. Add another thing that might make sense to formulate using a tool like a Satsolver. Did anybody ever hear of role-based access control? So when you have multiple users of some systems or resources, then you usually need some way to define which user or which user role has access to what specific resources. So some example might be this. We have a knowledge base resource, we have an accounting resource, we have some firewall resource. So very, very simplified company. This might be resources that they have in the company. And then we have different roles in the company. Some of the employees are admins, some are from the human resources department, and some are in the, I don't know, support team. So usually you don't want to give everyone in the company access to everything. So you define these kind of roles which group many people. So I don't know, the admins might be 2 or 3 different people, but they all have the role admin, and this means they are allowed to access the knowledge base, and they're allowed to access the firewall, and we don't give them access to the accounting. So that's something maybe only human resources should have access to the accounting of the company, but human resources might also have access to the knowledge base. But of course, we don't want human resources to configure the firewall. Similarly, for the support team, they need maybe access to the knowledge base to answer questions, but they don't have access to the accounting and to the firewall. So this way, we can define this in very different ways. This could be defined in some kind of huge role-based access tables, could be defined using some similar configuration languages that grant special privileges. But in the end, it would always kind of end up with, you could always draw this kind of table where you list the resources and roles, and then you can put in this table which role has access to which resource, right? And you can imagine that this is maybe getting quite tricky, but you might also have some constraints that are really important for your company, but they're not directly visible in this, or there's not like one check mark where you can say, well, this constraint is now satisfied. So there might be some constraints that every user with the role human resources or support must be able to access the knowledge base, right? This might be something that we want to sanity check our configuration with. So this is our configuration, and then we have some constraints, and we want to know, are they satisfied or not? Then only users with the role admin may access the firewall. This is a bit easier to check because it only mentions the role admin and the firewall. And yeah, we can see admin has firewall access, but nobody else does. So fine, that's satisfied and that's easy to see. But then no user may access the firewall and the accounting at the same time. Yeah, we can probably also see that by looking at those columns and yeah, making some conclusions. But if these roles here get a bit more tricky, we probably need some better way to check these constraints. So we should maybe first come up with a way to model what do we need to check these constraints? Do we just need to put these constraints in the SAT solver? Yeah, we also need to put this kind of table in the SAT solver, right? So because otherwise, what can we validate the constraints against? So we could just check whether they are maybe valid and then they're meaningless, but that's not very helpful. So basically, yes, we want to encode this table into the SAT solver. Now this table doesn't really look like propositional logic, right? Does it? So what do we do? Now, this is really a tricky part because usually there are many ways to encode this. So what are ways that you could encode this? Anybody has an idea of how to encode this table? So do you see anything here that is true or false? Yeah, you can basically see the okay and the, well, not, right? So should we make one Boolean variable for every cell? Okay, so let's, what do we name these Boolean variables? What would we name the variable for this cell? So like this cell is uniquely identified by admin and knowledge base, right? So we could, if we want one variable for this one, we could call this variable admin knowledge base, right? And this variable we could call admin accounting, and this variable admin firewall. How many variables would we then have? Well, it's basically 3 times 3, 9 variables, right? Now, let's say there's a new user role edit. This would add, well, 3 more variables. If I add a new resource, so the number of variables are basically always multiplying the number of roles with the number of resources, right? And that gets a lot. Now, okay, never mind.
One thing like admin knowledge base okay as a one variable and then take it into admin. So whenever we add multiple roles, so we don't need to add like a new role knowledge base true, new role account base true. Instead of that, we can make admin knowledge base okay as a one variable. Either it is a true or a false.
Yeah.
That one we can take it to multiple roles. So there is no need of more number of iteration.
No, but this one is also another variable, right?
Yeah.
And this one is another variable.
Yeah, that only like admin knowledge base okay is true as one variable.
Yeah.
Knowledge base not okay as one more variable.
For admin.
For everything.
For everything.
Then we can take the role and then assign it to particular, like whether it is a true or false.
I'm not. So how many variables then would you need?
For checking true or false, we need true variables. And we can take admin, HR, support, like those variables, how many we want.
Okay, so there's probably better encoding than multiplying them out, right? One other thing is, so I mean, this would be this like setting every cell as one Boolean variable. In theory, it's perfectly fine, and the SAT solver will probably handle it, right? But what does it mean for our constraints? The encoding of this table needs to be in a way so that we can encode also our constraints, right? So we have 2 things that we want to express, and 2 things which might be quite different. We have one which basically says, yes, this role has access, or no, this role doesn't have access, which sounds like, yeah, just put one Boolean variable everywhere. But this one is now different. How would we encode only users with the role admin may access the firewall if we would put one Boolean variable for every column? This means that for every cell, sorry, even for every cell. This means that we would have to list explicitly the variable names that do not have admin in them, right? So how many variable names would not have admin in them? That's many, right? Tons of them. Here, well, this times the number of resources and support times the number of resources and so on. And we don't really want to update our constraints every time we maybe add a new role, right? Because this constraint that only users with the role admin have access to the firewall, it should not change even if we add a new role user or something, right? So probably our encoding of basically the ground rules and the encoding of the constraints both need to be taken into account when we want to solve this problem. And this is where basically the kind of the software engineering meets the formal methods, because in software engineering, well, here it might be security, doesn't matter. We usually have some very specific problems and we have some very specific constraints that we want to express. And now, how do we use the formal methods tools in the right way to solve our software engineering problem, right? And that's the tricky bit. And this usually really requires some good thinking. So you already mentioned we can separate actually the roles from the resources, and then maybe derive these Boolean values by combinations of roles and resources, which probably makes a lot more sense, because then we can also talk about roles and resources independently, because there are different Boolean variables. So let's try this. Let's try to now model it using one Boolean variable for every resource and one Boolean variable for every role. Now, the thing is that we need to check, is this really independent? Does it make sense to have these Boolean variables? So is there a way that you could have multiple roles assigned to a person? And the answer is yes, usually yes. So if somebody needs to maybe take care of one system and takes also care of another system, they usually have assigned multiple roles. That's how the role-based access works. So one person might incorporate multiple roles, and then they have all the benefits or responsibilities of the different roles. Now, how do we express that these contents of the table now? So let's try that. Again, there are many ways to do this. Even if we have the variables given, there can still be tons of ways to write the formulas, but we have to make sure we write them in the right way. So, okay, so I start with isadmin.
Access table and not access approaches and not access.
I'll just check.
Access file.
Okay. So you're suggesting a different formula. Is the formula the same? So wait, let me copy it and then you're saying we just remove this center part, right? Okay, now we have two different formulas. Which one do we pick? Why? So the question is, what is important about these formulas? If these are two different ways, are these two different ways to say the same thing? This would mean that we have semantic equivalence between the two different formulas, which means that one semantically entails the other and the other way around. Is that true? So how do we check that? We said we can check semantic entailment by saying basically this implies that, and we check validity, right? And then if we want to check the other direction as well, we need to check that this implies that and check validity. So this might be the same thing as now if we want to check it at the same time, just going to put some parentheses that we're really implying the right formulas. So if we want to check it at the same time, we're just going to put the non-leaf and it's invalid. This means they're semantically not equivalent. So these two formulas are two different formulas in their meaning as well, not only syntactically. So which one do we take? Well, okay, let's try the first one. Okay, let's try the first one, right? Now, should we translate the other ones in a similar way? Okay, and so let's take the next one is HR implies okay. Then the last one. Oh. is support would imply access knowledge base and not access accounting and not access firewall. Good. Well, now we certainly have some more formulas. And how do we combine them? Do all of these formulas need to hold?
Checking it, I don't think.
So, I mean, now we have 3 independent formulas, right? We need to do something. Is it either the rules for the admin have to be in place, or the rules for HR, or the rules for support? All of them, right? All of these rules, they have to be applied. We're determining if you have this rule, then you have these access, right? So let's put an end between them. Now, should we check whether this is satisfiable? If it's not satisfiable, what does it mean? So we're lucky, it is satisfiable. Now, how do we read this answer? Resizing doesn't work. Okay, so we have an answer where now we have somebody who is an admin, who is not HR, and who is not support. So somebody who's just an admin. And they have access to the firewall, the knowledge base, and not to accounting. Sounds good? Okay, good. Should we also check validity? No? Just for fun? Is it going to be valid? No. Because there must be some, well, if it was valid, it's kind of yeah, meaningless. Okay, so some invalid assignment. We have an admin who has access to accounting. That's already the contradiction to the first one, right? Now, what happens? So let's say we're going to simulate. I'm going to add a specific person. And this person is an admin and also works in HR, right? HR maybe also needs admins. Not possible. Why not? The access level is different, yeah, but what if I want to have some kind of super user that has everything, all the rules? Sorry? So the problem is that you basically gave negative assignments for when there was no reason to give a negative assignment, right? Should we really give a negative assignment for we don't have access to accounting? This means that as soon as we are an admin, we will never have access to accounting. But that's not what the role-based access says. The role-based access gives basically only positive access to resources. It says if you're an admin, you have access to the knowledge base. We don't really know for accounting. You don't get the accounting access from the admin role, but you might get it from somewhere else. So I think this negation doesn't really work, right? So what do? We delete it and go back to what you suggested, right? So yeah, let's now give only positive grants. So support only gets granted access to the firewall. So let's look at our admin and HR. Now it works, right? Now somebody can have both roles. And they actually do have access to everything because the two roles combined would give you access to everything, right? Now, let's do some sanity check. Let's maybe define some person who works for the support. Okay, now, well, they're also admin. Yeah, maybe they shouldn't be admin. So let's say I want somebody who works for the support and is not an admin. So now this person is not an admin, works for the support. Anything wrong with this person? What? In HR, okay. But yeah, so let's say not HR. Good. So now this person is not an admin, not in HR, only a support person, but has access to accounting and the firewall. What's wrong with our encoding? How come this person now has access to stuff that it really shouldn't have access to, right? The person is in accounting, but what went wrong? How can this person have access to the firewall? Something critical like this, and to the accounting. Can write their own paychecks, right? Not good. So what went wrong? Sorry? We had this negation just in and we just kicked it out, right? Down here? No, there. But then we can't just negate it for the support guy and not do it for the... It's giving us the same thing, right? Because then it basically, if we have to do it for one role, we did a very systematic translation here, right? So the problem is that we used implication, right? Implication only says, if you are this role, then you must have these things true. But it never says that if you're not this role, then you don't have this access, right? So our encoding of this table is not correct. Yeah?
I think we should replace the implication by the if and only if.
Okay.
For admin. I think we could solve it.
We can try this, and we'll probably have more trouble. So, yeah. Let's say if and only if. So the trouble that we're going to have, I think, is if we now have what do we have now if somebody is because we don't have negations in the access. Okay, so let's see. Now what would we get? We have access to the knowledge base. I'm not 100% sure what happens if some roles exist that accidentally have overlapping patterns in terms of the rights that they have. If then this if and only if. So basically, if you have a role, I don't know, super user that has access to all the resources, then this super user wouldn't need to be an admin, right? But now you're saying that you have access to firewall if and only if you're an admin.
Yes.
And that would contradict the super user that might also have the same access to knowledge base and access to firewall without being an admin because they're a super user. Okay, so this thing is really not so easy. The trick that we could do is yeah, I think we instead of going by the role, we could go by the resource. And then we could say you have access to the firewall if and only if you're an admin, because then I think we don't have this issue with the super user, right? No. Okay, so sorry, in the super user case, we would have to update if it has a tick mark in the resource, we would have to update the rule for the resource. So we would basically go column based, and then we would not really have those conflicts anymore. So basically by linking the resource to the role and then putting a disjunction, so you only have access to the firewall. If you are an admin, you only have access to the knowledge base. If you're an admin or HR or support, then we would avoid this problem of the clashes. So basically, yeah, we would do it like on this slide, where we could say we link the resource to the possible roles. So you only have access to the knowledge base if you are one of these. You only have access to accounting if you're one of these, which is only HR. You only have access to the firewall if you're one of these, and that's only admin. So this way, we would not end up with the same issue that we would have overlapping, or that we could have multiple roles, because if we add the super user, we would have to add the super user in all of these. Okay, so we didn't really manage to encode the rules because we were trying to find the right encoding for the table, but this is really, really important, because you might think you have the right encoding, and then you find an example where, yeah, you don't. So we could have probably found some examples just by encoding those rules and then found some violations, but now we just found these by exploring manually some configurations of user roles. Okay, so I guess so this one will be in the next session, where it will be a bit more exercise based. So this was already like an exercise, but a large group exercise. In the next session, we will do a more individual exercise, so you can work in your groups of 2. And we will have a worksheet for the next session. So we will just finish these slides in the next session, which should take only 10 minutes because we're almost done. And then you'll work on this worksheet, and Shoaib will explain to you how these worksheets work. So mainly you will do stuff with this Limboole interface and encode, yeah, similar things like this. So see you on, well, Friday? Is it Friday? Yeah, Friday. Yeah, see you on Friday.